All right, let's continue with the optional practice test number 4. This is 2021. Just in case this is listened to in the future. Show that the velocity, okay, we're given a particle that moves along the y-axis. It's going up and down. So its position at time t is given by that y of t equals tangent squared, t squared times tangent 1 over t, and t is greater than 1. Show that the velocity of the particle at time t is given by this velocity function here for t greater than 1. What you can't do is what some of you tried to do is just say, yeah, I took the derivative and got the same thing. Essentially, that's what some of you did. You don't get credit for that. You have to at least explain what you did, show some work, so that they can believe you. But it shouldn't be that hard of a question. So we know we have to take the derivative to get the velocity function. We have to apply the product rule. We have to apply the chain rule. So some things like if you're going to describe this in words, you would want to include those in your description. That way, they understand that you know where things are coming from. And so if you just say, yeah, that looks good to me, they're not going to believe that it really made any sense to you. And I'm talking too much while doing this, so hopefully I didn't make any mistakes. That was a mistake right there. Does mine match? No, because I made a mistake because I'm talking too much. Oh, there's no t here because the t squareds cancel. So, all right. Moving on to part B, at time t equals 4 over pi. Is the particle moving toward the origin or away from the origin? Give reason for your answer. We talked about a direction of motion question the other day in class. We have to know where the position, where the object is, what position it's in, and which direction it's moving. Both of those things matter here. So y of 4 over pi is 16 over pi squared times the tangent of pi over 4, because 1 over t is the reciprocal, so I like how I didn't write tangent at all. Tangent of pi over 4. Tangent of pi over 4 is 1, so this is 16 over pi squared. And the important thing about that is that it's positive. Now the velocity at 4 over pi is, they gave you the velocity function, so this should be fairly straightforward to calculate, or at least you can't make the mistake of getting the answer wrong from having the wrong velocity function, because they gave it to you. And so let's see, again, tangent of pi over 4 is 1, so we still got 8 over pi. And pi over 4, or rather secant of pi over 4, is root 2. So this is minus 2 here, because we're squaring that result. Remember, cosine of pi over 4 is 1 over root 2, so secant's going to be the reciprocal, just root 2, and then square root 2, and you're going to get 2. And so now 2 pi is about 6 something, so this thing here is bigger than 2. 8 over pi is bigger than 2, so minus 2 is still going to give me a positive number. So what does all this mean? You want to say something like, well, since y is positive, since y of 4 over pi is greater than 0, the object is above the origin. It's a reference to the origin, right? Yeah, moving toward or away from the origin. So it's above the origin, and since v of 4 over pi is greater than 0, the object is moving upward. So the object is moving away from the origin. I don't know if you can see that on my screen. It went behind a little something or another. Something like that. Okay, they were actually looking to see that you got these two values, and then you wrote a sentence explaining yourself. Part C, and the last part of this one, the velocity of the particle time t is can be written like this. They did a little bit of algebraic rewrite because they're concerned that if they don't show you this step, this might be the one step that keeps you from answering this question well, and they don't want you to get caught up by that. It's 1 over t here, minus secant squared of 1 over t. I want you to take the limit as t goes to infinity. Now, the second part is the easy part, believe it or not, and I'll explain that one in a moment. I'm going to focus on the first part. And you're allowed to separate this into two separate conditions, and look at this part separately from the what's after the subtraction. This actually works out better because this works out to be 0 over 0, and you can just go ahead and apply L'Hopital's rule. You don't apply L'Hopital's rule to that second expression over there, so this becomes 2 secant squared 1 over t times negative 1 over t squared, all divided by negative 1 over t squared. This is going to tie together nicely. These cancel here. There's still a 1 down here in the denominator. Now notice we have secant squared of 1 over t. We got secant squared of 1 over t over there, and over here. So this is just as an extra factor of 2, but that's good, and it's fine. So we can do the analysis all at once here. And so the limit as t approaches infinity of 1 over t, the stuff that's in the parentheses here, is going to go to 0. That's just the hyperbola, so that's going to 0. Secant of 0, well, that's reciprocal of cosine of 0. Cosine of 0 is 1, so secant of 0 is 1. Square it's still 1. Multiplied by 2, this works out to be 2. All right, so what about our limit as t approaches infinity of v of t? Well, this is the limit as t approaches infinity of 2 tangent 1 over t divided by 1 over t minus secant squared of 1 over t. We just showed that the first part of this is 2. That's what all the work we did. The second part, well, as we just said, 1 over t goes to 0. Secant of 0 is 1. 1 squared still 1. So this goes to 2 minus 1. And the limit of the velocity function is becoming 1 as t approaches infinity. Oh, let's see, gasoline storage tank, filled pipeline, refinery, all this stuff. The amount of gas in the storage tank is twice differential function g. And then we got t between 0 and 10 inclusive. Values are of g of t in thousands of gallons. That's a key unit there that's needed. Select the time t here in the table above. It doesn't know that g double prime is positive. We'll need that later, at least the interval from 5 to 10. Use the data to estimate the rate of change of the amount of gasoline in the storage tank at 3 hours. Well, 3 is between 1 and 5, so we'll use that interval. We need to show the computations and indicate units of measure, which some of you didn't do. So we're going to need g of 5 minus g of 1. Well, g prime of 3 is approximately g of 5 minus g of 1 over 5 minus 1. Which is approximately, I know one of them was like 19 and a half, then 18 and a half. Over 4, which is 1/4. And you can leave it as 1/4. Just going to indicate units of measure. And some of you got this wrong. We went over this just recently. The numerator, what are the units on that? What did they say? Thousands of gallons. I think that was it. It's thousands of gallons. Let me go double check. Yeah, thousands of gallons. Down here, this is a change in time, so that's hours. And so the units over here are thousands of gallons per hour. It's that simple, ladies and gentlemen. Some of you keep getting it wrong. You're just being thick-skulled. You're being hard-headed. Come on. It's not that hard. From 0 to 10, exclusive, is there some time t, where g of t is increasing at a rate of 0.2 thousands gallons per hour. When they give you an interval like this, start with those values, just to see if you can get, for an average rate of change, the value they're looking for. If not, then you can go look inside of that. So 24 minus 22 over 10. And what's that, 2/10? What is that, 0.2? My dog is whining, I'm sorry. That's 0.2. That's exactly what they were looking for. So now we just got to make the MVT argument. And so what do we need to demonstrate the mean value theorem? We need the function to be continuous on the closed interval, differentiable on the open, and then all the rest of it. So let's go back up to the prompt. I'm sorry, I walked away, but still I'm talking you through this. Going back to the prompt for a moment, we know that the amount of gas is given by a twice differentiable function g, okay, between 0 and 10. So we could say something like this. Since g is twice, I'm going to abbreviate a little bit here, differentiable, g is differentiable, and therefore continuous. And I'm going to add on 0, 10 because that's where this function is defined like this. So I got differentiability and continuity all in that statement right there. So by the mean value theorem, there exists a value c in the open interval 0, 10 such that, and I'll switch to writing g prime of c is equal to 0.2 because I just did the work to show that the average rate of change is 0.2. So that means the instantaneous rate of change at some point will be 0.2. All right, moving on to part C. It is known that g prime of 5 is 0.5. Use the locally linear approximation for g at t equals 5 to approximate the amount of gasoline in the storage tank at t equals 7. Is this an overestimate or underestimate? Give reason for your answer. All right, so we need a tangent line, equation of a tangent line, and we're going to approximate at 7. So let's see. So they told us g prime of 5 is 0.5. And I got to go back to the table really quickly because I don't remember. At 5, we had 19.5. So g of 5 is 19.5. So the equation of the tangent line, stray marks everywhere, is going to be y is equal to 0.5 times x minus 19.5 plus, no, I'm sorry, going too fast, x minus 5 plus 19.5. And then the value of g of 7 is going to be approximately 0.5 times, I'm already doing the calculation in my head and I shouldn't. And this is equal to, well, 7 minus 5 is 2. 2 times a half is 1. So 1 plus 19.5 is 20.5. Now since, and they told us this, g double prime is greater than 0 on 5 to 10, g is concave up. So the tangent line is below the curve. And therefore, this is an underestimate. Because remember, when the curve is concave upward, the tangent line is below the curve. And so if I'm approximating some point down over here from the tangent line, the actual value is up here because the tangent line is below the curve. Flip it over, make it concave down, tangent line's above. It's an overestimate. And lastly, D, the rate at which gasoline flows out of the tank and into trucks at time t can be modeled by the function r, defined by r of t as 100t over t squared plus 4. R of t is a 100t over t squared plus 4. T is measured in hours, R of t is measured in thousands of gallons. Based on the model, I'm pausing because R of t is measured in thousands of gallons. So they made a mistake here. This should be in thousands of gallons per hour. If this is a rate, luckily they don't ask for units on this, but it says the rate at which gasoline flows out of the tank can be modeled by R. R is a rate function. R of t should be measured in thousands of gallons per hour, not in thousands of gallons. That wouldn't have screwed anybody up, though. This is me just being critical of them. But anyways, based on the model, t between 0 and 10 is the rate at which gasoline flows out of the storage tank. At what time is the rate at which gasoline flows out of the storage tank an absolute minimum? So we're trying to minimize the rate, okay? At what time is the rate a minimum? So we're going to take the derivative of r, and we can apply the closed interval method here. Okay, so let's see, low d high minus high d low over low squared. Now they, now what was I going to say? I lost my train of thought. Oh, yeah, they give you a point for just taking the derivative. So if you think to take the derivative, you're off to a good start. So r prime is never undefined. It's only undefined when the bottom's 0, but t squared plus 4 is never 0. R prime equals 0 when the numerator, that's going to be 200 t squared is equal to 0. I just want to simplify this a little bit. So 100 t squared plus 400 minus 200 t squared is equal to 0. So 0 is equal to, that's going to be a negative 100. So I'll move it over to make it positive 100 and then subtract the 400. Factor out 100. So get t minus 4 and then t squared minus 4. So we get t minus 2 and t plus 2. And so the only reasonable, we're looking between 0 and 10. So negative 2, just throw it out. That's a possible solution here, but it's not part of where we're looking. So there's only one critical number between 0 and 10. So you could argue this from the first derivative test for absolute extrema, because you could look from 0 to 2 and then 2 to 10 and figure out that this is a absolute max. You can say r prime of 1 and r prime of, I don't care, 9. And then if you want to do that calculation, you can. The denominator is always positive. And so if you look at the simplified version down here, in case you didn't see me put those parentheses in, that looks terrible. Down here, if you plug in 1, you're going to get a negative. You get less than 0. Plug in 9, you're going to get a positive. So there has to be an absolute minimum at 2 because the derivative is always negative before 2 and always positive after 2. Or you could just test using the closed interval method and figure out that that's the smallest. If you go back to R, you plug in 0, you're going to get 0. How is that 0? I'm sorry. I'm just pausing for a moment. If you plug in 2, you're going to get 200 over 16. Did they want a maximum, and I read this wrong, and I'm a little bit off somewhere. It may be my fault here, but I'm going to just finish this thought. So this is going to be 1,000 over 104. I got to go back and look at the question again because now I don't remember. Oh, it's looking for a maximum. So I was thinking 0 is the min. No, how did I get these backwards over here? We should have a positive and a negative. So what did I do wrong? Oh, I know what we did wrong. That's okay because I moved everything over to the other side. I flipped the sign. I should be looking back up at here in this one. I did it after too much simplifying. If I plug 1 in here, we're going to get 5 times 100, which is 500 minus 200. That's positive. And if you plug in 9, you're going to get 81 and 4, which is 85. So 8,500, but now you're going to get 81 times 2. That 200, that's going to be larger. So this is going to be negative. So we do get a max here because the derivative is always positive before and always negative after. Notice how I got the answer of a minimum, but the question said max, so it means I must be wrong somewhere. I mean, they could be wrong, but don't go that route. Think maybe, maybe I made a mistake, which I did, and so I had to go back and fix it. And then the closed interval method shows this is less than 10. This is certainly more than 10. So this one is going to be our largest value right here. Just got to write it in a sentence. All right, ladies and gentlemen, that was fun. Go study.